One of the main goals of artificial mathematical intelligence is to develop a cognitively inspired software being able to solve mathematical problems at any level of abstraction, starting from school, university, even graduate problems, open problems in mathematics. In particular, this AMI software would be able to help broader scientists in the parts of their research which correspond to a mathematical modulation. Regarding formal evidence for AMI, we were able in previous years of co-invent, of co-discover different notions in several fields of mathematics. Within the co-invent project, we were able to discover the notion of prime ideals over a multiplicative ring, which was a kind of very technical notion due to Krull. And we were also able to co-discover notions similar to the complex numbers. Quasi-complex numbers was a previous years of some colleagues of mine. Also the notion of quasi-integers. We were also able to develop not only single definitions but also almost entire theories within formalizations of conceptual blending. For example, we were able to develop the seminal notions of fields and Galois theory by using many first-order formalizations of conceptual blending. For instance, we were able to co-discover in a new way the notion of field, the mathematical notion of field, the notion of a field extension, the notion of group optomorphisms of a field, and the notion of a meta-Galois group when the extension is a Galois extension. In addition, we were able also to co-discover the notion of Goldbach rings and the notion of commutative rings with unity with a compatible divisibility relation. Our general plan for the fulfillment of AMI consists mainly of three stages. The first one is what I call new cognitive foundations of mathematics. In this stage, we want to be able to classify the most important cognitive abilities, the most basic cognitive mechanisms our mind uses in order to be able to create mathematical ideas. One of the most outstanding examples is formal conceptual blending, analogical thinking, case-based reasoning, metaphorical thinking. On the other hand, more domain-specific cognitive abilities would be conceptual substratum, syntactic generalization and particularization, inductive and abductive reasoning, among many others. Then the idea is first to identify the most important ones and find also initial logical formalizations of them. On the second stage, we want to study specific mathematical proofs belonging to several sub-areas of mathematics, like for instance algebraic geometry, algebraic topology, commutative algebra, number theory, measure theory, real and complex analysis, among others. We want to study specific proofs there, and we want to know how the cognitive abilities that we identified in the previous stage of the project would fit, how they could came together, in which order, in which way they are structured in order to be able to generate these proofs. After having enough evidence, we want to use the formal framework of the canonical, so to speak, meta-mathematical theory which study proofs, which is called formal proof theory, which is a subfield of mathematical logic. We want to study to use the formalisms of formal proof theory in order to be able to find particular formalizations of these proofs into this classical formal proof framework. Now, in the last stage of artificial mathematical intelligence, we want to write the global pseudocode, the global algorithm for AMI. For that, if it's required, we want to use stronger frameworks like institution-independent model theory or category theory, among others, in order to get a stronger, a more solid framework, a more solid algorithm. And then we want to test the initial version of algorithm in specific mathematical areas like number theory, real and complex analysis, measure theory, and topology. We want to test it, and we always want to offer as an output a human-style schematic proof. A proof which gives these are the main concepts, and we use these former cognitive abilities of, for example, conceptual blending or metaphorical reasoning. We use it indeed in that way. We combine it in these specific ways, and then we obtain the proof or the solution to the conjecture that the researcher or the student in the school or the student of the university or the PhD candidate give as an input. We always want to give human-style proofs for that.